What's going on, guys? It's been a while since I made a video. In this video, we'll take a look at how to find the initial solution to a transportation problem using the northwest corner rule. Reading from my right, we notice the northwest corner rule is one of the three methods in obtaining the initial solution of a transportation problem. Now, the usual objective of transportation problems is to minimize the cost of shipping goods from the origins to the destinations. This figure over here illustrates a transportation problem from which a transportation table can be derived. So we can see we have the origins, that is the nodes where they are axed to a destination. And these acts have a cost, that is a value that are assigned to transport a good from the supplies to the demands. So each act has a cost associated with it. So to transport any good, it comes with a cost. I am of the assumption that you have prior knowledge. So let's go straight to solving our example. The values filled in here represent the cost for each unit shipped or transported from the origin to the destination. So the cost for each unit shipped from the origin to the destination. The northwest corner rule is very similar to the game of Sudoku. So you might see us playing some Sudoku in here. I've redrawn the structure for the sake of clarity. In my clear structure that I've redrawn, unit cost we had from the table are the values represented on the top right corner, the values in brown. Now using the northwest corner rule, let's play Sudoku. In Sudoku or in the northwest corner rule, the sum of the values on the row must be equal to the total value at the supply side. So in this case, we have the supply side being 5. And again, the sum of the values on the column must be equal to the total value at the demand side. So the demand side here we have 7. So we are going to choose between 7 and 5. Remember, the objective of the transportation problem is to find the minimum cost. So we want the minimum value between 7 and 5. We are going to choose the minimum, which is 5, and put 5 as D1. Now the total value on that row is supposed to be 5. So we are done with the first row. Now on the first column, the total value is supposed to be 7. So we can fill O2 with 2. So we have the total of this column to be 7. Now these two affect the second row. The total on the second row is 8. So I can fill D2 with 6 to make the row 8. Now this 6 also affects the second column. The second column has a total of 9. So I can fill O3 with 3 to get 9. Now this 3 value affects the third row, and the total on the third row is 7. To get 7, I fill D3 with 4. So I get the total on that row to be 7. Now this 4 affects the D3 column. It affects the 18. So to get 18 on the D3 column, I put 14 here. And this 14 affects the O4 row. That is the fourth row. So I put 14. So I have 14 here. So I just leave it as it is. It's all equal to 40 because I have 14 in the 14. So how do we find the total cost or the initial solution for this transportation problem? Very simple. You find the total cost by multiplying the total cost by the values that we determine. So we have the total cost equals 2 times 5 plus 3 times 2 plus 3 times 6 plus 3 times 4 plus 4 times 7 and plus 2 times 14. The product of these values summed is going to give us 102, and that is going to be our total cost. So the initial solution for transporting the goods from the origin to the destination is going to be 102. So as I said, the main goal of the transportation problem is to minimize the cost of transporting goods from an origin to a destination.
Never stop.